Hi everyone. Today I'm going to be reviewing the material from the first part of chapter 13 in your textbook, Investigating the Relationship Between Two Variables. I'm going to focus our conversation on an introduction to this topic, and then I'm going to show you how to do a cross tabulation and also to calculate the statistical significance for cross tabulation. So in a way, you'll see that this lesson is building on some of the material we covered in chapter 12, and it's showing a specific way to approach hypothesis testing. Okay, so you can describe the relationship between two variables in a number of different ways. First of all, something that we've talked about before is you can speak to the direction of the relationship that you expect. So we've talked about this before, a positive relationship in which the two either increase or decrease together, or a negative relationship in which is one in which when one variable increases, the other variable decreases. Another way to talk about the relationship between variables is the form of the relationship. Often in political science and other disciplines, we assume that there's a linear relationship between variables, but as we'll talk about later, that might not always be the case. And then also we can talk about the strength of the relationship. So we know that they vary together in some way, possibly taking on a linear form, but how strong is that relationship? How consistent is that relationship that we're seeing? So those are some of the ways that we're going to consistently talk about the relationship between two variables. And then later, as we move into the next chapter, we'll discuss how we can talk about whether a relationship is causal. So that's important right now. We're talking about relationships in terms of correlation, how they vary together, not speaking about it in terms of one causing the other. So this is just a figure drawn from your textbook, looking at the different types of correlations that we can see between variables. So you can see what it would look like to have a strong linear relationship versus a strong negative relationship. The one thing you'll notice too is that when we're plotting these relationships, you see the x-axis, symbolizing the independent variable, and the y-axis as the dependent variable. So that's why you've heard me talk about using that language before, x representing independent variables and y representing dependent variables. And then this is a figure from your textbook as well, speaking to the strength of the relationship. So what would it look like to have a strong linear relationship versus a weak linear relationship? Of course, we see these are both in the positive direction, that they're increasing together. But the one that really forms a more consistent shape of the line, that's showing a stronger relationship than the second example. So the different measures of association indicate the extent to which two variables are related. And each level of measurement of the variables has different measures of association that are appropriate to calculate. So again, that's why I keep bothering you guys with levels of measurement, is because it doesn't go away. We have to know and be comfortable with the levels of measurement of both our independent and dependent variables to know which measures of association are going to be relevant for our research design. So this is also a table drawn from your textbook, just to give you some ideas. So it's summarized in the first column. We see your type of dependent variable. So if it's quantitative, we're thinking more ratio or interval level data. Sometimes it could also be ordinal level data. But then we're seeing what also is sometimes relevant is the type of independent variable. So if you had something, for the first example, if you had a dichotomous independent variable, something perhaps like gender, then you had a ratio level dependent variable, you might want to do a difference of means or a difference of proportions test. So for instance, that would have been relevant to my example I was using for statistical inference last week when I was talking about the rate of receiving the death penalty based on gender. So I had that dichotomous independent variable, and I had a quantitative dependent variable. So I could do a difference of proportions test as one of my measures of association. As we move down to the last couple of rows, you'll see that that's where we see linear regression and logistic regression. This is going to be our goal for the semester, to have some sort of regression model in our final papers, and there'll be more to come with that. But as you can see, what's important here is the type of dependent variable. So if your dependent variable is ratio, interval, even ordinal level, you can do a linear regression. But if your logistic regression is a dichotomous variable, say for instance like voted or did not vote, then you would be using a logistic regression model. So I know those terms don't really mean much to you right now, but I just want to point out again why it's so important to know our levels of measurement, because that's going to lead you to the appropriate measures of association for your final paper. So something that's appropriate for nominal level variables and also ordinal level variables is a cross tabulation. And I think these are really interesting, so I wanted to go through an example today, and then I'll also be showing you guys in SPSS how to do a cross tabulation and to test it for statistical significance. So the point of today's lecture is to just understand what a cross tabulation is and what the statistics are telling us. And then I'll show you, shortcuts if you want to do this yourself for your final paper. So just to begin, a cross tabulation is a table displaying the joint and relative frequencies of two categorical variables. So these are either nominal or ordinal level variables. This is not something you would want to do with ratio level data. So what does that mean, joint and relative frequencies? I'm going to walk you through some examples so you can see what that means. So what you begin by doing is you separate the cases into groups based on their values for the independent variable of interest. And then for each grouping of the independent variable, you can compute the frequencies or percentages that fall in each level of what you're considering the dependent variable. So again, this is very similar to a frequency distribution, but you're just looking at two different variables at the same time. Hopefully this will make more sense when I show an example. And then once you have this in place, you're going to decide whether the frequencies or percentages differ from group to group. So are we seeing some sort of relationship? And if so, by how much? So this is an example when doing a cross tabulation, we always put our independent variables as the columns and our dependent variable, what we consider our dependent variable, as our rows. So you can see here that we're looking at the relationship between gender and party identification. If you look down the columns, you can see that they each equal to 100% with a little bit of rounding errors. So how you would read this table is that out of the individuals surveyed, 11.9% of men identified as strong Democrats. 15% of men identified as weak Democrats. 20.9% of females identified as strong Democrats. 16.2% of females identified as weak Democrats. So it's allowing us to see the breakdown of party identification by gender. And just by looking at the raw numbers, we start to think that there could potentially be some sort of relationship between gender and partisan identification. Just to show another example, and this example was coming from the National Election Survey, and I put as the independent variable ideology, just measured as liberal, moderate, conservative, and then the dependent variable is how often someone prays each day. So you can see that all of the independent variables total to 100%. And then when we read the other totals, like we can read across the first row and see, okay, 27.9% of individuals pray 7 times a day. So 18% of liberals pray several times a day, compared to, 41.4% of conservatives. So we can see potentially some patterns going on in this example as well. So the next thing I want to talk about is, okay, we think we're seeing some patterns, but how can we test our cross-tabulation for statistical significance? So we can say that there's a statistically significant relationship between gender and partisan identification. So what we're asking, and this goes back to what we were talking about with statistical inference in general, is we're saying, do the observed relationships reflect true patterns, or could they just arise from chance, maybe be unique to our particular sample? So just some vocabulary from your textbook. Statistical independence, a property of two variables in which the probability that an observation is in a particular category of one variable and a particular category of the other variable equals the marginal probability of being in those categories. Okay, so if you're anything like me, that doesn't make a lot of sense when you just read it. And I need to kind of to see what that means using an example. So this is a little bit more simple of the example I started with, but just to help us understand what statistical independence means. So in this particular example, our independent variable is gender, just categorized dichotomously as male and female in this example. And our dependent variable, also a dichotomous variable, meaning only two choices, and that it's this is nominal level, is voted and did not vote. So first of all, what we're going to look at is, what is the probability of being male? So in order to do that, we look down and we see that there's 100 males total. Hopefully you can find that at the bottom of the second column. And out of 300 total participants, which we see at the bottom of the last column. So the probability of being male is 100 divided by 300.33. Next, we look at the probability of voting. So we see that if we look across the first row, last column, we see that 210 individuals surveyed voted out of those 300 individuals total. So the probability of voting, much higher than in real life, but in this example is 0.70. So then we calculate what we call our marginal probability. So we take the probability of being male and we multiply it times the probability of voting, and what we get is 0.23. Next, we compare our marginal probability to our joint probability. So in this research design, how many individuals actually were male and voted? So to get that number, we look at the second column of the first row, and we see that 70 men voted. So 70 out of our total 300 equals 0.23. So this is an example where our joint probability is the same as our marginal probability. So that means that gender and voting are statistically independent, because the probability of being in both categories separately equals the actual joint probability of being in both. So we're seeing in this example that there's no statistically significant relationship between gender and voting. Okay, let's take one more example just to make sure that this makes sense. So in this example, our independent variable is social class. Very simply, it's being categorized as upper class and lower class, and our dependent variable is the same, voting and did not vote. So what we're going to do is calculate the marginal probability of no vote and being in the lower class, and then compare that to the joint probability to see whether the two are statistically independent. So if we want to know the probability of being in the lower class, we look to the bottom of column 3, 150, and we divide that by 300, the total number of participants, and we get 0.5. Then we next look at the probability of not voting. So we're looking at the second row all the way across, and again it's 150 divided by 300, 0.5. So that again is our marginal probability. Our next step is when we multiply those together, we get our marginal probability of 0.25. So next what we do is we compare that, the marginal probability of being in the lower class and not voting, to the actual joint probability. So to find our joint probability, we are looking to the second row, do not vote, and then comparing that to the third column of lower class, and you see that we have a 100. So 100 over 300 is our joint probability of 0.33. So again, this is an example where the variables are not statistically independent. And we know this because our marginal probability that we calculated does not equal our joint probability. Okay, so how can we then test that cross tabulation for statistical significance? So in our hypothesis testing last week, we knew that we needed to find a test statistic. And because we were using a linear regression model and our n was greater than 20, we knew that the test statistic that was appropriate for the quiz last week was the t-statistic. The test that's appropriate for testing a cross-tabulation for statistical significance is called the chi-square test. And I'm going to go over with you guys how to calculate by hand the statistic. I'm never going to make you do this, so don't get worried, but I just want to show you how it works so that you can get a good idea of actually kind of what's going on and really why this statistic makes sense. Okay, so I already said that, sorry. So again, what we're trying to see here is that same thing. Are the two variables independent or dependent at a statistically significant level? So this is when we move into hypothesis testing and, can we reject that null hypothesis of the variables being dependent on each other? So if we see a chi-square of 0, that's going to imply complete statistical independence. So obviously we're going to be looking at something higher than that. Okay, so my example, by now we should hopefully be getting more comfortable with reading across tabulation. So my independent variable in this example is male and female. We see that represented by our columns. And then our dependent variable is opinion by gun control, which we see represented in the rows. So again, your columns total to 100%. And then we can see we have both the percentages and actual numbers of our data. So we can see in the far corner that the N is 1,201. So that's how many people have took this in the National Election Survey. And just by looking at the numbers, we can see that there does seem to be a relationship going on between gender and opinions on gun control. But again, we want to see if that relationship that we think we're seeing is a statistically significant one. Okay, so how do we calculate the chi-square statistic? This is where it gets a little bit complicated. But the first thing we would want to do in order to calculate the test statistic is to calculate the expected frequencies of being in each category. So what we do is we take the row total and multiply it times the column total and divide by n. Okay, so what does that mean and what are you looking at here? So if you could just look at the first row for me, you see under male, it says 252.96. That's the expected frequency for the category, a lot more difficult, male. How we get that number is we take, again, that column total. So for the 582 men times the row total, the 522 individuals that said buying a gun should be a lot more difficult. We multiply those by each other and we divide by the total, which again, our total number of respondents, 1,201. So each of those numbers, that's the calculation that we had to do. So just one more example to make sure we're on the same page. The 269.04 under female, we got that by taking, again, our column total, 619, times that row total, 522, and then dividing that number by the total number of participants, 1,201. So that would be our very first step in calculating chi-square, is that we need to have all these expected frequencies. Then the next thing we do is, this might seem very, very similar to you to how we did our standard deviation. We take our observed frequencies. So these are the actual number of individuals that actually fell into those categories. And then we have our expected frequencies, and we take the difference between the observed, what we actually saw, and what would be the expected given those totals that we just did. And then, so the difference between the two, that's being represented right now in my third column. The next step, again, very similar to calculating the standard deviation, we then square those differences. And then the step that's different is that we take those differences squared and we divide by the expected frequency. So again, those were those expected frequencies that we calculated in the slide before. And that gives us our last column. And then we take the differences squared divided by the expected frequencies, that, fifth column, and we add those all together. So you'll see at the very bottom of my slide, I have 62.20. This is actually my chi-square statistic. Oops. Okay, sorry. So then we have that number, and again, so this would be similar to like the homework example where you took your beta divided by your standard error, and you have your t-score, which is 1.96 that we were looking for. So now we have to know, what value of the chi-square makes it so that the relationship is statistically significant. So something we need to know for this is the degrees of freedom. So that's a new term that we haven't used before, but it's something we see in some statistical tests. How we know the degree of freedom for our crosstab is we take the number of rows in our cross tabulation. So again, the number of rows is corresponding to the number of choices in that dependent variable, and the number of columns, which is the independent variable. So it's number of rows minus 1 times number of columns minus 1. So for this example, sorry, I switched it up, but we had 2 columns, so 2 minus 1, 1, 5 rows, 5 minus 1. So our degrees of freedom in this example is 4. So the next thing we would have to do then is to look to what is Appendix C in your textbook, which I can show you a visual. Later. But in my textbook, it's on page 621, and I see that there's a chi-square distribution, which is interesting because it looks pretty normal. It's pretty close to our normal distribution that we talked about last week, but a little bit different. So once I know my degrees of freedom, I can use this to look up what value I would need to be higher than to have a statistically significant relationship. So if I want it to be statistically significant at the 95% confidence interval, then I want my p value to be 0.05 or less. So looking at this chart, I can see that my critical value that I'm looking for with 4 degrees of freedom is, if I want to be 99% confident, I guess that's what I was doing here, it has to be greater than 13.28. Wow, so mine is much greater than that. We calculated 62.2%. So I can be highly confident. Looking at this chart, I can be 99.9% confident that gender and support for gun control are not statistically independent. I can reject my null hypothesis in this example. So let me just stop the screen sharing for a second. I just wanted to give you a peek at that table I was looking at, and just in case it's a little bit different in yours. So I was using the 4 degrees of freedom, and that's how I was able to look it up. But anyway, I'm going to show you guys on OnCourse if a crosstab would be something you're interested in doing for your own research, especially those of you guys who have some really interesting ordinal level variables. Perhaps you did a survey design. A cross-tabulation might be a great fit for your research project. So I'm going to be showing you how to do a cross-tabulation in the SPSS program, in which they will calculate the chi-square statistic for you and let you know if it's statistically significant. But I just wanted to give you guys a little bit background on how that calculation is made. So that's my lesson for today. Thank you for listening. Bye.